But this evening's talk is about the Parker Solar Probe. Oh, that's interesting. Oh yeah, the Parker Solar Probe. Now this is NASA's latest mission, okay, and it's a spacecraft that will fly closer to the sun than any spacecraft has done before. So the previous spacecraft that studied the sun, the nearest they've got was back in 1976, and that was looking at the sun from about the orbit of Mercury. This is going to get 7 times further in. And the aim is all about understanding not just our star, but the environment that our Earth lives in. Because we don't just live on our own without interference from the sun and the rest of the solar system. So you're going to learn a bit more about how the sun affects us here on Earth. And this is really interesting because you could say that solar astronomy is about the only branch of astrophysics that has everyday relevance to your life. Okay? Most of it is all going on at a distance. But no, this is stuff that from day to day can affect your life here on Earth. So, we are completely dependent on the sun. It's our source of energy, all our heat and our light that affects the habitability here on planet Earth. And the trouble is that with all this great stuff, the sun also brings some potential hazards. Now, it may not be obvious to the unaided eye. I mean, the sun looked particularly beautiful this afternoon, but the sun can unleash huge weather storms that can buffet the Earth and can cause great problems in our technological era. So the sun is a very average star, okay, in terms of its mass, its temperature, its chemical composition, its age, its size. But compared to the Earth, it is extreme. Its mass is extreme. Its temperature is extreme. Right in the centre, it's some 16 million degrees. Even on the surface, it's just short of 6,000 degrees. Now, if you've got matter at that kind of temperature, I mean, you may have heard the idea that the sun is just a big ball of gas. Well, if it's going to be at those kind of temperatures, it isn't really a gas. It's another state of matter that we call a plasma. And the thing about a plasma is it's so hot that it's not made up of little atoms, but the atoms have, there's so much energy in them, they've broken apart into their nuclei and their electrons. So it is an electrically charged gas. And this is what we call the plasma. And that is what makes studying the sun so complicated, because electrically charged gases don't behave like normal gases, and especially electrically charged gases at this kind of temperature. So this is, you know, more the view if you look through the ionized light, so the sort of excited atoms, as it were, excited electrically charged particles of the sun. And the reason that it's interesting is that the sun is not just a great big ball of plasma at extreme temperature, it also has a magnetic field. It has the strongest magnetic field of any object in the solar system. Now, at its core, it looks a bit like the bar magnet that underlies the Earth. It's got a north pole and a south pole. And the field lines from the north and south poles stretch way out of the sun. They go right out to the round of the planets, right out into the interplanetary medium. But it's not that simple. You don't just have this bar magnet. But you've got to remember, the sun is rotating. It rotates once on its axis about once a month. And not just that, it rotates faster around the equator than it does around the poles. So it kind of gets twisted up around the middle compared to the poles. And then under the surface of the sun, driving a lot of this energy, taking the energy from the core, bringing the heat to the surface, you've got big vertical churning motions. And between this twisting up around and the twisting up and down, all the magnetic fields get knotted. So instead of a nice simple bar magnet, all across the surface, you've got knots and tangles in the magnetic field. So here's a picture, more or less showing you what those magnetic fields at the surface are like. And we can take an image, we can take a picture. I know you can't usually take pictures of magnetic fields, but here we know where they are because magnetic fields and electrical gas, plasma, are coupled together. So if you have a strong magnetic field, an electrically charged gas follows along the lines and traces out the lines of the magnetic field. And if you have a charged gas moving, it generates more magnetic field. So the two are tied together. This is why I say it doesn't flow and behave like a normal gas. is confined and affected by the magnetic field. And this is just a picture in the ultraviolet. I'm telling you it's the surface of the sun. It may not look like the surface of the sun as you know it. It's in the ultraviolet, which picks out gas that's at tens of thousands of degrees. So the surface of the sun is dark, but the charged plasma that's going up along the loops and down is somewhat hotter, and so it's giving off the ultraviolet light. Now this I'm talking about as the surface of the sun, but it's not like the sun has a nice determined surface like the planets do, or the rocky planets do. This is the visible disk of the sun. It's visible because it's at 6,000 degrees, and something at that temperature gives off light in the visible, in the optical spectrum. Now, beyond that, the atmosphere of the sun extends out. It extends out another couple of million kilometers, but it's very thin and it's very tenuous. And the interesting thing is it's also very hot. Now, you can't see it because it's very faint. If it's tenuous, I just mean all the particles are very thinly spread, so there isn't a lot of light. But you can see it if you're ever lucky enough to see a total solar eclipse. When the moon moves in front of the sun and blocks out its light, and if you ever see one of these, then one thing you note is that this outer atmosphere, what we call the corona, pops into view. So here you can see the moon's disk is covering the sun, and all the structures of this corona stretching out. And one of the mysteries of the sun is, even though the surface is at 6,000 degrees, this corona is at temperatures of a couple of millions of degrees, 2 to 3 millions of degrees. And we don't understand that in the space of, less than, I don't know how many, less than 1 million kilometers, a lot less, it goes from being the surface at 6,000 to this phenomenal temperature of up to like 3 million degrees. There's an extra source of heating at the surface of the sun. And there are all kinds of theories as to what it could be. Now, the material out in these outer layers, a lot of it's so hot it's not actually giving off optical light. You'd really need an X-ray or a UV telescope to see it properly. And the thing is, because it's so hot, the particles are moving very fast. They are not so easily tied. Even though the sun's got a huge amount of gravity far out here, they're travelling so fast that they escape the sun. So the material in the outer corona blows off continually and forms something that we call the solar wind. And material is leaving, at speeds of like 400 to 800 kilometers per second all the time. And that means you've got billions of kilograms per second just flowing out from the sun. It may seem a lot, but remember the sun is so incredibly massive, that's nothing. The mass lost from the surface of the sun is nothing compared to the mass of the whole sun. And all of this material from the corona leaks out and expands and blows out and fills up the solar system with this solar wind. Now it diffuses out, it's more concentrated near the sun, it drops as it goes out. By the time it gets to the Earth, it's about 5 particles per cubic centimetre. So it's not like the space out between the planets is vacuum, it has got about 5 particles per cubic centimetre, and that is coming from the sun. And if you want to see the solar wind in action, you really need to move to ultraviolet, to X-ray wavelengths. Here's observations where they cover the sun's disk with, it's like a pretend moon. You just cover up the disk so the sun doesn't blind you. You've got an ultraviolet picture of the sun, and then this is ultraviolet pictures at different wavebands. But can you see material just streaming off the sun, and every so often you get a big gust that spreads out. Now this is sped up. I can't remember how many days worth this is, but this is going on all the time, material just streaming from the surface. And again, these occasional large bursts and flows. So this is happening all the time, and it's fueling the solar wind. And as it spreads out, and it meets the planets, it meets Earth, well, we don't actually feel too much of an effect because we're buried within our magnetic field. We've got a magnetic field which again stretches out above the Earth's surface and protects us in the magnetosphere. It's got a special protective sheath. And the charged particles get deflected by our magnetic field. Sometimes if it's strong, you might get magnetic field out here, tail wear, reknotting, and particles coming down the pole and producing the northern lights. So if the sun's very active, giving off a lot of particles, that's when you get to see the aurora borealis. Not necessarily from Cambridge though. So this goes on all the time, and this is mostly harmless. This is just normal space weather. The thing we have to worry about the sun is that it has space storms. So we have events on the sun which are signalled by a flare on the surface, where gas is heated up to temperatures of tens of millions of degrees. It gives off very bright flashes of very energetic radiation, the ultraviolet and X-ray. So here's one just brewing here. So you've heated up the gas, and it produces this bright light, and they can last from minutes to hours. That's just a very quick one. And it sends this radiation out. And this is very damaging radiation. It gets to reach the Earth 8.5 minutes later. Now again, we're usually fine because we're within the Earth's magnetic field. If you're an astronaut out above, say you're travelling to Mars or something, or elsewhere in the solar system, you're going to have a problem if you get a blast of this radiation. So this is, first of all, a flare that is signalled here. And where this energy comes from, you remember I showed you those pictures of all the magnetic fields coming up, getting tangled and knotted. The thing about magnetic fields is you can store energy in them. It's like a rubber band. If you stretch the rubber band and twist it and stretch it, you can store a lot of energy in it. But at some point, you're going to have to let go of that rubber band, and all the energy is released in one go, and then it goes back to its original configuration. Same thing's happening with magnetic fields. You can stretch it and store energy, and then suddenly they ping back, and they release all that energy. And when they do, that's when you heat this gas, produce this flare. But the other thing that happens is this catapults a lot of the material that's been held and entrained in those magnetic fields out into space at phenomenal speeds. So here you have some of the knotting, you have some material that's been drawn up along the magnetic field lines, it re-knots underneath it, and the energy release just hurls out this blob of plasma out into the solar system. And again, at huge speeds. Speeds of perhaps up to like 1 million kilometers an hour. And these travel out. And these are the things you need to worry about, because if these coming out, so we've got the flare, and then later this blob of plasma starts travelling out. Now, most of the time they miss the planets. This is just to slow down. Again, billions of kilograms contained in one of these clouds. And this is electrically charged particles all tied together by a strong magnetic field, this cloud of plasma. And most of the time it might miss us. But we need to worry about what happens if one of these hits the Earth. These are called coronal mass ejections. And the last time we know that one hit the Earth was in 1859. At that point, there were effects in telegraph offices, like the wires caught fire, or they operated without any electricity supply. There were aurora borealis seen down in the Caribbean. There was a magnetic storm. All kinds of extreme things happened. Today, if one of those happened, it would be very different, because now we've got electronic satellites. So not only do you have the radiation, but then up to, it could be half a day to a couple of days later, you get this blob of gas hitting you. And you need to be prepared for this coming, because if it hits the Earth, it really rattles and shakes our magnetic field, and any satellites are in danger. Just to show you, we had a near miss a few years ago. I think it was back in 2012, and there were a couple of satellites, stereo A and stereo B, staring at the sun, and there was this cloud is coming straight to the satellite, and you see all the static afterwards. That's all those fast charged particles, those high energy particles hitting the detector, and this is looking at the outburst from the side. This satellite didn't have a direct hit. And again, just to show you some of the damage that was done to, that you get in the detector. So think about this. You've got all our infrastructure that depends on communications satellites and the electronics, things like GPS. They all stand to be damaged if something like this hits them square on. And you've also got the potential, perhaps, of disrupting the power grid if this creeps up, and as will happen sooner than we expect. So we have got lots of reasons to try and understand and start to predict these kind of events. And also, again, you've got damage to any astronauts outside or at the periphery of our magnetic field. Just to say, this solar storm back in 2012, it hit this satellite, it passed through where the Earth had been 9 days earlier. So that's what I'm saying by that was a near miss. So Parker Solar Probe is going to go down towards the sun, and it's actually going to fly through the outer atmosphere, through the solar corona. And the idea is to study the solar wind and these flares and these injections. And it needs to go close to the sun. Now, this may be surprising because, we can stand back here and we can look at the sun and see what it's doing. But if you really want to understand the energy, the structure, the behavior of the solar wind and these flares, by the time the solar wind comes out to us, it's travelled for 3 or 4 days. It's got mixed up with other stuff in the interplanetary medium. And so you've lost a lot of the character, it's lost a lot of energy, you've lost a lot of the things that define the physics of what's going on. So it's much better to study the plasma just as it's being released from the surface of the sun. So by going closer, we see what's happening at source. So the aims of the probe altogether are, first of all, to look at that problem about the coronal heating. How does it go from 6,000 degrees up to millions of degrees over such a tiny kind of physical space? What is the heating mechanism? Now, we think it's connected with the magnetic energy knotting and re-knotting, but we need to test that, and there are various theories that predict different observations. So we're going to fly through the corona itself, and as they go fly through the corona, they're going to detail the structure, the dynamics, the wind pattern, and the behaviour to discriminate between the two different, various theories. So you're going to understand this coronal heating problem, because that is probably tied to what is causing the flares and these mass ejections. And this is all tied to how magnetically active the sun is. But the interesting thing is, can we make predictions? Okay? If you can work out the behaviour when these are released, and you can see what was perhaps happening on the sun beforehand, and also if you can work out what's causing the acceleration of the particles, where the energy source is, you are learning a lot about what causes these, what triggers them, and the idea is that you will not just understand the sun better, but you'll be able to start predicting space weather. The idea is that once you have predictions, you can see the sun might be brewing one of these storms, and if that is right on the centre of the disk and it's facing towards Earth, well, actually let's just take action. Let's perhaps do things to mitigate any possible damage. You could put satellites in safe mode. Maybe you can do things to the power grid so that if the storm did hit us, it wouldn't be quite so much damage. And so it's mitigation, it's making weather predictions, but weather predictions on a small scale. There's so much, it's so difficult to do weather here on Earth, trying to predict weather on the sun and then how it affects us a few days later here on Earth is quite a challenge. And of course, the last thing is also understanding the sun. The sun is a very average star. And by understanding what is particular about the sun and its activity, we learn about other sun-like stars out there. And this is crucial because it all goes back to the question of habitability. You may have heard of the fact that Proxima Centauri, the nearest star to us, has got an Earth-like planet around us. It's a fairly sun-like star, but it's much more magnetically active. Even though it might have a habitable planet, that star has got so much more flares and stuff that would render any planet around it probably inhabitable. So by understanding the sun, which has got life around it, we can then perhaps look at other stars, their characteristics, the likelihood that any planets around them could be habitable or rendered inhabitable by that solar activity. And of course there's also the study of the plasma. Again, we study the sun because it's our nearest representative star, so it's the easiest one to look at in detail. But plasma is something that's very difficult to study in the lab at temperatures of millions of degrees with these kind of magnetic fields. But here we have, right next door to us, 150 million kilometres away, we have a nice lab. We have the sun. And by looking at how plasma behaves, we understand plasma physics, and that helps us understand where else it's in the universe, like when it's swirling around black holes, or when it fills the space between clusters of galaxies. So there's a physics, understanding basic physics that's also involved, and just using the sun as our lab. So to do this, the Parker Solar Probe was, and it's, by the way, I should just say, the name Parker comes from Eugene Parker. This is the first time a spacecraft has ever been named after a living person. It's quite cool. Eugene Parker, I think he's 91 this year, and he was the astronomer who first posited the idea of a solar wind. So I think it's quite a nice honour to have the probe named after him. So here it is, 12th of August. It gets launched on a Delta IV heavy rocket. And it's about the size of a small car, and it's buried in the cone now. For some reason the sound now has decided not to work again. You just have to imagine the countdown. 4, 3, 2, 1, and here you have it blasting off. And that's quite a launch, right? So again, you're launching something the size of a small car, and in the nose cone you have this beast, and this is the probe. And the probe goes from about there upwards. The rest is just to keep it safe and settled during the launch. Now, it's going to do about 24 orbits of the Sun over the next 7 years. And it'll make the first approach of the Sun just at the end of this month. Okay? And the first data from the first pass of the Sun will come back to us in December. Now, it's going to get to within 6.2 million kilometres of the Sun's surface. That doesn't sound a lot, does it? That still sounds big. Right, now just imagine, right, here's the Sun, here's the Earth, the space, and I put them a metre apart. The spacecraft is going to go about 4 centimetres from the surface, so about there. I think that's pretty close. Okay? So 6.2 million kilometres may sound massive, but it is really, really close. And it's about as close as we can get and still have the spacecraft survive. And as it goes past the Sun, it's going to be the fastest human-made object, travelling at near 700,000 kilometres an hour. Okay, I think that means it could get. You could get from New York to Tokyo in under a minute. That's quite cool. However, I don't think you would want to be riding the spacecraft so close to the Sun. Now, you will see previously we've got as close as Mercury. So here we're really getting to the interesting bit. We're getting close to the Sun, we're getting close to where the solar wind's being released. We're studying all this energy at source. But if you go close to the Sun, okay, that raises a few particular challenges for building a spacecraft. The one thing is actually getting it there. This may not sound obvious, but it's very difficult to fly things in towards the Sun, because the Earth is going around the Sun. Here we are, Exhibit A. There's the Earth. It's going around the Sun at 30 kilometres every second. So if you launch a rocket from the Earth, it inherits that sideways speed of 30 kilometres per second. Now, it's not like you can just shoot the rocket in the opposite direction, because we can't fly things at 30 kilometres per second from Earth. The best we can get is about 11 kilometres per second to escape Earth's gravity. So you can't undo that sideways speed unless you're very canny. And what you do is you fly it past Venus, and it's going to do about 7 fly pasts of Venus. And each time, the gravity of Venus is going to pull in it and slow it down and shrink the orbit. Well, not slow it down, but it's going to change the speed, and it's going to shrink the orbit down, and it's going to get closer to the Sun. It's going to make the first Venus flyby happens on the 3rd of October, by the way, and it's about here currently, and it'll swing around the Sun at the end of October. So not only have you got to get there, but the spacecraft has to survive when it's there. So the first thing is that it has, just to go back, I told you that radiation and the plasma from the Sun can damage electronics. So here you've got very elliptical orbits. And what it does is it takes data just as it sweeps through here, and then it has a rest. And then it takes data and sweeps through here. So it just does a tiny bit of data collection when it's going right through the corona, and then you switch off the electronics. And only when it's a long way away from the Sun around this bit of orbit do you relax and then beam up and send the communication back. So you're not using the communications when you're really close to the Sun. And it's also got to survive the heat, not just the radiation, and it's got a large hexagonal shield that's about 2.3 meters in diameter, about 12 centimeters thick. It's painted white on the top, and it's made up of a special sort of carbon foam composite. And that can withstand enormous temperatures. It's going to be about 1400 degrees that close to the Sun. This is designed to withstand those temperatures and keep all the electronics and the instruments down at about 30 degrees behind the foam shelter. So the radiation is like, almost 500 times that we receive at Earth. So you've got the hexagonal shield, and that should withstand up to just under 1400 degrees, so that should be okay. The other thing you will notice, is that acts like an umbrella. So as it goes past the sun, it swings that in front of it, and so it will follow behind that, and it will protect the instruments. And the other thing you notice, it's got swing ring solar panels, right? Solar panels can't withstand that amount of radiation, so they get swept back and protected. So the panels themselves, when you're away from the sun, they collect the energy, but it's too much when they're too close, and they swing back behind here. And in fact, even close to the sun, there's too much energy. These are too heat sensitive. So there's all kinds of mechanisms where they run water through the solar panels to absorb the heat, and then run it through the radiators to evaporate the heat. All of this kind of thing is needed to keep this spacecraft alive. And then finally, you've of course got the instruments themselves. Now, most of them are behind the shield, but of course, you've got a few bits. There's a little sort of particle collector here that just sticks out around the edge to sense what particles are there. And you've got antennae. And so these are two of the experiments. And you've got to be very canny to make those of materials such as niobium and molybdenum, which have got melting. These have got some of the highest melting points, like over 2,000 degrees. So all the electronics, even not just the instruments, but the electronics that take the readings from the instruments back to back into the spacecraft, they've got to be made out of these very rare, very robust materials. And even the wires, as I say, are made from niobium. So altogether, it's carrying 4 instruments. It's going to, there's an imager. I'm afraid you're not going to get pretty pictures. There's this big screen in the way, this big heat shield. So even though it's going really close, you're not going to see pretty images. These images are going to look out to the side. So they're going to see these flares as they expand out from the sun, and see their structure in detail from the side. You've got sweep. That's what that little cup is at the front that just pokes out above the solar shield. That's looking at the particles that make up the solar wind, the low energy ones. So the things like protons and electrons, it's counting them, how fast they're going, how they're behaving, and what direction they're going. Then you've got something here, IOSIS, which is looking at the high energy particles released in the flares, again looking at their behaviours and characteristics. And then finally, with all those properties, they're mapping those to sensing the electric and the magnetic fields that are going on around the sun. And it's matching all of these together. They hope they're going to understand the behaviour of the sun. So we don't know for sure it's going to survive. I mean, looks good. But, this is really challenging technically. It's a precursor for more missions. This is the ESA, European Space Agency Solar Orbiter, that's due to launch in February 2020. So I think they're going to see how the Parker Solar Probe gets on before they launch, in case they need to tweak some things. Now this isn't going to go as close, but it's still going to go much closer than the previous best, well within the orbit of Mercury, and this will take images. So if you can wait to 2020, then you'll get close-up images of all the structures on the sun's surface. Anyway, I hope I've whetted your appetite. Watch the news come December when the first results come from the first week past the sun. And hopefully, as you can see, I think this is something that will have great benefits for everybody here on Earth. Thank you very much.